Okay. Right, so last lesson we introduced Turing machines. This whole idea that if a problem is solvable, it can be solved using this very simple system, where an infinitely long tape divided into squares, and on those squares can be any character. That character then moves left or right, is read by the head, and then based on the state the machine is in and what it's read, it follows rules to change the tape, change the state, and move in a direction. And any solvable problem can be solved using that simple system. It's considered a fully abstracted computer. If a Turing machine can do it, a computer can do it. If a Turing machine can't do it, a computer can't do it. That led on to the topic of unsolvable problems. Some problems are unsolvable. They can be mathematically proven that there is no solution to it. That's not the same as an intractable problem, which is a problem that can be solved, but on current hardware, it would take too long. And that's pretty much where we got to with that. So what I want to do today, so it should be a relatively short lesson, because at the end of this, I think we'll pause on the new stuff and we'll do some revision, because we still got mocks of the last week. And I'm just ask people to let me know what topics they want revisiting. But to finish this one off, I'm going to have a look at if you get a big question on Turing machines. So this is an example of it. We'll go through one together, and then I'll export one of these and stick it in a download so you can have a go at it. Right, so this is a odd question, but we should be able to get somewhere with it. It says two important components of a Turing machine are the transition function and the tape. 5 components of a typical modern computer system are a DVD-ROM, as you can tell how long ago this was written, compiler, main memory, processor, and the program. Complete the table by writing into it the numbers of modern stuff. This is a really complicated way of asking which of these modern computer components are equivalent to the tape and the transition function in a Turing machine. So the transition function, which of these, DVD-ROM, compiler, main memory, processor, and program, are the modern equivalent of the transition function? Stick your ideas in here. I'll load Teams as well in case we're still having issues with. So Adam reckons the transition function is equivalent to the program. Anyone agree, disagree? Adam also reckons the tape would be the main memory. Is everyone else stuck on this? Okay, can't seem to get into Teams one. I have to hope the chat here works. Yeah, it will be. The transition function is essentially the instructions of what to do, which is what a program is on a modern system. And the tape is equivalent to main memory because that's the thing that is being read and updated as the Turing machine works through the transition function. The next part, explain the relationship between the Turing machine as a model of computation and an algorithm. That's a tough one for a 1 mark question. I think where it's going with that is trying to point out that a Turing machine follows instructions to achieve a purpose, which is what an algorithm is. Let's have a look what it says. Oh, right. That was a really badly worded question. I can't imagine many people got that one. It says, if and only if an algorithm exists to solve a problem, then a Turing machine can be designed to solve the problem. Yeah, it's a way of saying that the Turing machine can solve any solvable problem. If an algorithm exists, then a Turing machine can do it. And then we get the kind of big question that you could reasonably get on it. In a minute I'll export this and I'll put it there on Teams for you to download. If I can get into Teams, I'll have to restart it. Have a go at this in a bit. So this is the transition function. So what this means is if we're in state SB and we're reading a 0, then leave it in state SB, leave it as 0, and move 1 to the right. If we're in state SB and we read a 1, then leave it in SB, leave a 1, and move to the right. So this is similar to mine, it's just moving to the end first. And these are all those ones. And what the question then does is it sets a diagram of a Turing machine up and says this is how it starts. After 8 steps, it looks like this. So trace the computation of the Turing machine from step 9 onwards using the transition function. Show the contents of tape. So what it asks us to do is to say, well, this is step 8, we're here, we're looking at a 1, and we're in state SF. So we look at the transition function to find out what would happen next. So we're in SF and looking at a 1. So there's SF and looking at a 1. So on the next one, it would need to be in SF and a hash, and the arrows move there. So we'd fill in here that we're still in SF, that 1 has been replaced by a hash, and now the arrow is pointing here. Does that make sense? So having run through that, it then wants you to try and explain the purpose of the Turing machine. Having run through it, can you figure out what that Turing machine did to the input? Okay, I've uploaded that to the Teams Year 12 Computer Science area. So could you have a look, see if you're able to download it from there. If you can't get it, drop me a message. I'll see if I can find another way to submit it. If you could download that, you can then be doing it pen and paper, or however, it's a big question for me to try and display on the screen all at once. So could everyone have a go at that? And then just post a comment in here when you're done. Once enough people have posted a comment that they're done, I'll go through it and we'll see if you got it right. So download it from Teams, have a go at it, post me a comment when you're done. So each time we need to decide what to do, we have a look at what the current tile is that's being read on the tape, and we look what the current state is. We then find the transition function, the delta function that applies to that, and read off what it should be. So the first one, it's currently reading a 1, and we're in state SF. So there's the delta function that applies, state SF and reading a 1. And it says, leave it in state S1. So I can put in here, sorry, it's leaving state, oh no, go to state S1. So go to state S1 as that says, put a hash in the place and move that way. So now it will be pointing there. This will all stay the same, so that'll still be hash, hash, no, that won't have changed. So that's where we should be after 1 step. Is that what everyone put for your first step? Okay, I'm glad Aidan did. Anyone else? Okay, good. So now we're looking at a hash symbol and we're in state 1. Whoops. So we find the delta function that applies to that. So let's find a state 1. There we are, state 1 and hash. There it is, it's this one up here. So that says stay in state 1, leaves as a hash and move to the right. So this will stay the same. Still in state 1, and we've moved to the right. So that's where we are after the next cycle. Exactly the same again. We point here, still in state 1. So now we're in a different position, we're pointing to 0 in state 1. So here's state 1 and 0. So it says stay in state 1, leave to 0, and move to the right. So move to here, leave it as a 0, leave it in state 1. Now we're in state 1 looking at an empty block. So state 1 empty block is here. Go to state R. So go to state R. Where are we looking at state 1 empty block? Put it as a 1. So that 1 goes here. And then move that way. So now we're pointing here. And all this, of course, stays the same. Okay, and that's where we are. So is this what everyone was doing so far? So up to this point, does this match what you've been doing? Can I have a yes or no, please, not just ignoring me? Okay. Oh, welcome, Ryan. Add you to the register. Oh, and Tom. Stephen here yet? You weren't here at the start. Anyone still missing Stephen? No. Okay, so rather than just carry on the whole thing, I'll show you what the mark scheme says for this so you can check yours, because we know the system now. So this is where the marks come from. So 1 mark for getting those 2 right. That's the moving to the right with the hash symbol. 1 mark for those 2 right. 1 mark for those 2 right. 1 mark for those 2 right. Try and make all that visible on the screen at once if I can. There we go. So yeah, have a look at that. See what you got for it. And then, did anyone figure out the purpose of this particular Turing machine? Well, let's have a look back at the question there. So we started off with a 1, 0. We ended up with a 0, 1. And by the looks of it, it goes all the way to this end. It picks up that one and carries on until it finds an empty one and then puts it down. So I'm wondering if it's just swapping it the other way around. Haven't done the whole thing, it's hard to tell. Let's see what the mark scheme says. Yeah, just reverses it. So it went all the way to the end, picked up the 1, took it all the way to that end, went all the way to that end, picked up the 0, took it all to that end. So it's essentially flipping them round. But it's a 1 mark question, that one, so if you're not sure, guess. If the input was 1, 0 and the output was 0, 1, reversing them is probably a decent guess to go for. Let's have a look. these. Oops. Yeah, this is the next part anyway, good. A Mealy machine has an input and an output for each of the transitions. And that's what we need to use to do this. So looking at this, this is just a transition function. And let's see how it would work. So let's say our, let's get to some drawings. So let's say our tape is 1, 0, 1, 1, 0, and we're pointing at this one, and we're in state 0. That's the current state of our Turing machine. And we need to know what to do next. Instead of being given a transition function in that format, we're given this finite state machine. Well, we're in state 0, so we know this is the state we should be looking at. We know we're looking at a 0, so we choose the output that starts with 0. So in that case, it's this one. So this is the path we need to follow. So this output 0 moves to the right and leaves us in state 0. So on the next line, it would be 1, 0, 1, 1, 0. Now pointing there, and still in state 0. Now we're pointing at a 1. Well, it turns out here, same thing. If there's 1's an input, it leaves us in this, leaves us a 1 and moves to the right. Once eventually we're pointing at the gap here, then it will take us to state 1 as well as outputting a gap and moving to the left. So it's exactly the same setup, it's just a sort of visual way of showing it rather than the transition function. Let's get rid of that for a second. So if I go back to the exam question, there we are. That's not the one I wanted anyway. Keep going. That's good. I might set that one afterwards actually, because that's taking a transition function and then asking you to complete a finite state machine that shows the same thing, which is quite nice. I'm trying to find one. There was one 2 years ago. I'm hoping it's on here. Yeah, there we go. Oh, same thing. It gives it as a transition function and then says, well, here it is as a finite state machine. In fact, I think I'll export a bunch of these and upload them for you to all have a go at. I'm trying to find what it just gives. It was 2 years ago. It's not on here yet. Okay. So what I'll do, just to finish this one, there's a couple of things. I'm going to export a couple of these questions. I'll post them on